So, for linear, Newton's second law is force equals
You're right. I'm sorry.
mass times acceleration. Now, what we saw last class was that for rotation, everything is basically the same as linear, just with different symbols. Now, that's kind of the same with Newton's second law, and so that's what we're going to be exploring today with Lab 10.2, is how Newton's second law will apply to rotation. Okay? So, I want to go over, before we go any further, the answers to that stuff from last class, because the answers to the stuff that we did last class, like the explore at the end of class, is going to help us with what we need to do today. So, that, we're going to come back to that equation here in a second. But we're going to answer these questions as a class so we're all on the same page. And so that's why I wanted you to get out your notes from last class, is so that I can okay? So, Steven, pick a random number. 17.
Every single
Why are you going over here?
freaking time.
Alright, Josh. This is the easiest one, so
So number
ripping
one.
the band-aid off. Here we go. Alright, so how does torque relate to angular acceleration?
I put, what I got from the explanation was the more torque, the more angular acceleration.
Yeah, that's basically it. So when you say more torque, what is an appropriate way to have said that? Like, starts with an N.
In?
Yeah. Like, think about the system. Like you have
Net
torque on
torque.
one side. What?
Net torque?
Yes. Okay. Perfect. So the more net torque, the more angular acceleration. So yes, that would be correct. Okay. So remember last class you were moving those weights over, and that's what you were doing to change the net torque on that pulley to change the angular acceleration. So cool. More net torque, more angular acceleration. What was torque proportional to? Distance was one thing, yeah.
Yeah. And
But specifically, what kind of distance?
From the center of rotation.
Angular.
It's
From
the
the
alpha.
distance from the center of rotation.
Okay.
And what else is it proportional to?
Force.
Force. What kind of force? Applied force. Any kind of applied force.
Yeah.
Okay, so technically, from this, if torque is related to angular acceleration, then that shows you that a force applied is also related to that angular acceleration. Okay? How does adding mass to that rotation arm affect your acceleration? Josh, pick a number. 22, all right. But like you might have singled you out on that one.
Well, it like went a lot slower.
So the more mass you added, the slower. Ooh, yes. So yeah, more mass on that rotation arm slowed the acceleration, and so that's one of the main things we're going to be exploring today, is what that mass is actually doing to your system. So I want you to know that relationship now going into this lab, because it's going to help you a lot figuring out some stuff. So yeah, more mass on that rotation arm, the slower that acceleration is. And then last, well actually we have two more. We're going to talk about that exit ticket as well. But for 3, pick a number. 13. Alright. So, how would you find your angular acceleration from a graph of angular velocity versus time? And slope. Perfect, yeah. Because remember, velocity versus time, slope was acceleration. Same with this. Angular velocity versus time, slope is angular acceleration. Awesome. Okay, then the last thing was the exit ticket last class, which was the relationship between, or like what the slope represented from a angular displacement versus time graph. So for that, pick a number. 6. Alright.
No team, thank God.
So, if the slope of an angular velocity versus time graph is angular acceleration, what is the slope of a angular displacement versus time graph? And pick on somebody
Would it be angular velocity?
Yes. Yeah, so slope from angular displacement versus time is angular velocity. And the slope of angular velocity versus time is angular acceleration. So that graph, last class, kind of did this. So what's happening to our angular velocity? I don't like the way you worded that. It's increasing. I like that better.
I said
So it's increasing. So angular velocity is increasing, which means it is accelerating. Okay? So how would you describe what's happening? Like, how do you know it's increasing from looking at the slope? What's the slope doing? It's getting
big.
bigger, yeah, steeper, I like better. So the slope is getting steeper. So notice how it's kind of flat here, meaning your angular velocity isn't very big. And it's getting steeper and steeper and steeper and steeper and steeper. So that means it's getting faster and faster and faster and faster and faster, meaning it's accelerating. Okay? Now we can talk more about the lab now that we went over that. Okay. So in this lab, we're trying to figure out how Newton's second law applies to rotation. That's like the whole big thing for this lab. Is like, how does this apply for rotation? And so we did this stuff last class, so you could kind of see some relationships, but now we're actually going to derive those relationships today. So we're going to do this in 2 parts, because I find it easier for you to do part 1, then we come back together to talk about it, and then you go do part 2, because everything makes a lot more sense if we do it that way. Anyway, so I'm going to go ahead and tell you what the 2 parts are. So part 1 is to find the relationship between torque and acceleration. And then part 2 is to find the relationship between something called the moment of inertia and acceleration. Now, you don't know what moment of inertia is yet, because that's the thing that we're going to be talking about after part 1. So, anyway, write it down, we'll get to it. Anyway, so part 1 is
Inertia is the property of mass.
what's up?
You said relation between moments of inertia and what?
Moment of inertia and angular acceleration. Okay. Whenever we determine a relationship between 2 things, what do we do?
Make it the
Graph. That's exactly what we're going to do. We're going to be making a graph. Okay? So which of those 2 things could you directly change? What were you changing last class? The torque. Right, how are you changing the torque?
Adding mass.
Adding mass. You weren't really adding mass, you're just kind of like
moving it.
shifting the mass, I guess. So yeah, shifting the mass is how we're going to be changing torque today. So you kind of already know how to do that. So that'll make this go a little bit faster. Yeah, so to change torque, shift mass. Okay. I'm gonna give you the mass of the washers and the mass of the little like hangy thing on the other side, so you can actually calculate your torque. So to calculate your torque, what equation do you use? R what?
Force supply. Force supply.
Times force supplies.
Sine.
Okay, so for the R, it's going to be the radius of the disc that that string is hanging over. Your force applied is the force of gravity from the mass pulling down. Okay. Now you need to find the torque on one side, find the torque on the other side, subtract them to get your net torque. Does that make sense? Okay. And then your theta is actually just going to be 90 degrees because it's acting perpendicular to the pulley. And so theta of 90, or sine of 90 is what?
1.
1. So that just kind of goes away. Okay? So that's what you're going to be doing for torque. Now, if you're changing torque, is that your independent or dependent variable?
Independent.
Independent. Yep. The thing that you change is your independent variable. So where does that go? X or Y axis?
X.
Perfect. Right? To get acceleration, it's going to be a little bit more complicated. You're going to get angular acceleration graph. We're going to be using, I forget what they're called.
Angular
Lab
velocity.
pros. I don't know. Some little device. It's going to give you a graph of angular velocity versus time, and from that you can find the acceleration. So if you graph angular velocity versus time, how do you find the acceleration?
This way.
Slope. Okay. So your graph should look something like that when you graph it. Just pick 2 points, find the slope. I'm going to show you how to do this with the actual device. I'm going to hook one up, walk you through it so everybody's on the same page. Okay? But that's basically what I want you to do. You're going to do 5 trials and then use alpha.com to graph. Now, this graph is going to be on your lab. This is going to be a major lab, and so you're going to have to do this a more fancy way than Calcula.com. But for today's purposes, so that you can see a slope and a number and stuff like that, you're going to use that Calcula.com just for like in-class purposes. Okay? But what you can use for your lab to make your life a lot easier is to use Excel. If you don't have Excel at home, I have computers and I have tutorials. So, oh, and your homework 10.2 is to do your graphs for this lab. So you need to have all your graphs completely finished for this lab by next class. Okay, now the lab doesn't due until Tuesday of next week. But the graphs I want to see completed by next class. Okay?
Yes.
Okay, so that's all I'm going to tell you for part 1. You have a question?
After today, will we have all the information to complete the lab?
Yeah.
Okay.
All we're doing is the lab today. We're going to be done with the lab today, what you need from it, and then you do the rest at home. Okay, so remember you're changing the torque. You need to calculate the net torque. So calculate torque on both sides. Subtract them, find your net torque. Then you need to get the acceleration from a graph of angular velocity versus time. You do that for each of your 5 trials. So you're going to need to make a data table. Okay? I'm going to leave it up to you to come up with your data table because you should know what you need in your data table at this point. Okay? So I'm going to start not holding your hand so much. So 5 trials, use Calcula.com when you're finished. When you start to graph it using Calcula.com, call me over so I can look at your stuff and see if everything went okay and discuss some stuff with you. Okay? Other than that, I'm going to give you, let's see, we get out of here in an hour, right?
Yeah.
So I'm going to give you, I don't know, take 25 minutes. Okay, 25 minutes should be plenty of time.